In this video, I'll be showcasing my mini brush drone project inspired by Max Imagination's tutorial. Although the drone is able to lift off, the controller is still a bit sensitive and difficult to maneuver. This is an area of improvement for the future. This project uses an Arduino Pro Mini for the drone, an Arduino Nano for the controller, and two NRF24 radio modules for communication. For the motor drive, I'm using 41 and 4148 diodes, SI2300 N-channel MOSFETs, and 10 kilo ohm resistors, and 4 brush motors. Each of these motors are rated to be 19,000 kilovolts. Also for the NRF24, I've added a 10 microfarad electrolytic capacitor. Otherwise, I have issues with loss of signal that prevents the drone from being controlled by the controller. And also, I was suggested to use 100 microfarad electrolytic capacitor for the MPU 6050 by a user named Robert. This did help with the resetting issue of the drone. Also for the battery, I'm using 3.7 volt 450 milliamp hour battery, and has a 30C discharge rate. The higher discharge rate the better. I found that anything below 25C would not be enough to power all the components of the drone. And for the propellers, I'm using 35 millimeter propellers in diameter. I find that the bigger the propellers, the larger the surface area, and thus the bigger the thrust. Previously I was using smaller propellers, which wasn't able to properly lift off the drone. Regarding the PCB of the drone, I started with creating a sketch in Fusion 360 to sketch out the shape of the drone, as well as the controller. Once I have a sketch, I converted that to a DXF file, which I was able to import into EasyEDA to form the drone boundaries. And after that, I just placed the components and started the traces. In terms of the design choices, I placed the motor driver in the bottom layer. This was suggested by Max Imagination, such that there's a copper area separating the motor driver and the Arduino Pro Mini and MPU 6050. This was an excellent choice because it reduced the resetting issue from the drone in my previous prototypes. Essentially, the copper area acted like as an EFM blocking shield, EMF blocking shield, created or generated from the diode in the motor drivers. So that helped a lot. In terms of the traces, I made the power lines a bit thicker than the rest of the lines. So for example, this power line here is set to 0.45 millimeters, but the rest of the lines, such as communication lines to the NRF24, are set to the default width to 0.254 millimeters. Furthermore, for the NRF24, I avoided the copper fills around this region. It was actually suggested by electronoobs to avoid any copper areas around any radio modules to reduce any noise. And then furthermore, I also avoided 90-degree traces. So this was sort of a convention that people have been following, and it's also good to keep that consistent as well. Yep, so the same idea is followed for the controller. Thicker power lines, um, no 90-degree traces, um, and then I use Fusion 360 to sketch out the controller shape and then exported that to as a DXF file and then imported it here. And this is how the PCB for the project was created. And here is a 3D view of the project, which helps show what it would look like if it was printed. And for the controller, so yeah, I printed the joystick values in the serial monitor. Um, the calibration process is to find the minimum, medium, and maximum values of the joysticks. Medium values can be found by leaving the joysticks untouched. Its natural resting state is in the middle, and the values printed here currently are the medium values, and I've reflected these values printed onto the software here. Then to find the minimum and maximum values, you would move the joysticks all the way to one side until it reaches its minimum value and or its maximum value, and you can see that being translated here. For A6, it went all the way to 0 on one side, and then on the other side all the way to its maximum value at 1023. And it appears that for all of these joysticks, the minimum and maximum values are the same. And this was my process for calibrating the values of the controller joysticks. The software of the drone, I did had to modify these lines, which was responsible for mapping out which motor corresponded to which physical orientation. For example, motor 0 mapped to the front right motor of my drone, motor 1 to the front left, and so on. However, in the previous code, it was set to this, but it did not correctly map to my drone because I had used different PWM pins for my physical wiring connections to the motors. My wiring connections here are as shown. However, in the code, it was commented that motor 0, the back right was connected to pin D9, motor 1 to pin D6, motor 2 to pin D5, motor 3 to pin D3. However, I have wired the back right motor to D3, a front right D9, back left D5, front left D6, and so because of that difference, I had to modify or I had to retranslate these mapping to match my own configuration. You can actually find some comments left out to show which motor mapped to which pin here. So if you search up motor 0 and scroll a bit up, you can see this if statement under Pro Mini, which is the MCU that I'm using. It says that motor 0 is actually connected to pin 9, and there are some comments for the other motors there as well. The way that I found which motor, motor 0, 1, 2, 3 corresponded to which physical orientation is that I had to go to the right motor function, and just under this line I commented this out and then made a quick test for setting motor 0, for example, to 1200, and this spun a very specific motor, and from there I was able to deduce what motor 0 mapped out to my drone. In this case, it was the front right motor, and I did that for the rest of the 3 motors. And lastly, in under config.h, defined mid throttle to 1050 to match this comment, which is close to what I'm using since I'm using a brush set of motors. On the multi-week configuration, another thing to note for is to ensure that the IMU values are correctly translated when the drone moves in various orientations. For example, if I try to move this drone around, you can see that the multi-wii correctly translates these movements for yaw, pitch for example, and roll. So it's just good to test that these movements are being translated correctly. Also, it's good to simulate these movements as well, so that the drone is able to correctly capture that in the software. Also, in order to reduce shaky movements from the drone when on the air, uh, one thing I tried was to reduce the p-values for the roll and pitch here, and also the rate and expo I set to 0.50 and 1. This was suggested by Max Imagination in his video tutorial. Another good test measure is to verify the MOSFET's integrity in the motor driver. To do this, I measured the voltage at the drain. Um, since this is an N-channel MOSFET, as the gate voltage increases, the voltage at the drain should approach zero. This would make sense because the drain is connected directly to the negative pin of the motor, and the source is connected to ground. Here is a demo showing this scenario. Once you've tested that the MOSFET is operational, but you find that the motor is still not spinning, another good check is to test the voltage at the um, motor pins. Check if the voltage increases as you throttle up. If it does, then the issue could be due to the motor. This actually happened to me that the motor wasn't spinning, but the voltage was received at those terminals. So after I replaced the motor, um, it it fixed the issue. I was able to verify that the issue was the motor. What happened to that motor was that it did burn out due to excessive use. Lastly, in order for consistent motor operation, test that the PWM pins output a frequency that's consistent at each four motors. When I tested each of the PWM pins at the Arduino at Mega, I found that the frequency outputted a constant of 8 megahertz.